Hi everyone, today we're looking at how to synthesize Verilog designs using open-source EDA tools, all on the Crucible Workbench. This walkthrough shows you the full flow from writing code to producing real hardware logic, with no tool installed by hand. It takes the guesswork out of digital design and helps you verify your work before hitting silicon. We'll go through each key step so you can follow along on your own machine. Let's start by setting up the environment. Let's kick things off by initializing our project with a simple Igny init command. Next, we spin up a dedicated environment called Demos, keeping our EDA tools neatly isolated for this project. We create our workspace, pointing it to a new counter directory and linking it directly to our Demos environment in one seamless step. Let's move into our newly created counter workspace. And just like that, the Explorer reflects our fully configured project, ready for development. With the project and workspace ready to go, our foundation is set. Next, let's install the EDA tools we'll need for synthesis. With our workspace ready, let's pull in the EDA tools we need. A single command installs Icarus Verilog for simulation. Next, we grab GTK Wave, which will let us visualize our simulation waveforms. And finally, Yosys for synthesis, giving us a complete open-source flow in seconds. With all three tools installed, we clear the terminal, and we're ready to dive into the design. With the EDA tools successfully installed, our environment is fully ready to go. Now let's take a closer look at the Verilog source files that make up our design. With our environment ready, it's time to bring in the design files for our counter project. Let's expand the counter directory to see everything we're working with. First up, My Counter file. This is our core Verilog module defining a simple 4-bit counter with clock and reset logic. Next, we open TestBench file, which drives the stimulus and verifies our counter behaves exactly as expected. Then Top ties everything together as the top-level module for simulation. And here's Yosys commands.cl, our synthesis script that automates the entire Yosys flow. Step 1. Read Verilog top.v parses our RTL source into Yosys. Step 2. Hierarchy. Check. Top elaborates the design hierarchy and sets top as our top module. Step 3. Proc converts our always blocks and if-else logic into internal muxes and registers. Step 4. TechMap maps. That down to Yosys' internal generic gate library. Step 5. dflibmap maps. Our flip-flops onto real cells from the NAND standard cell library. Step 6. ABC optimizes the combinational logic and maps it to NAND cells too. Step 7. Clean strips out any unused cells and dangling wires. Step 8. Emits the final gate-level netlist. With all the files reviewed, let's head back to the terminal and put them to work. With the source files reviewed, we're ready to put the design to the test. Let's move on to compiling the Verilog and running the simulation. We kick off the compilation by running iVerilog through Igny, bundling our counter design and test bench into a single executable. Next, we execute the compiled simulation with VVP, again seamlessly managed by the Igny CLI. And just like that, the simulation runs and delivers the output directly to our terminal. Notice the fresh count.vcd waveform file instantly appearing in our Explorer, ready for analysis. With the simulation successfully compiled and executed, our results are ready to be examined. Let's open GTK Wave to analyze the counter's waveforms in detail. To visualize our simulation results, we simply run Igny run GTK Wave on our generated VCD file. GTK Wave launches instantly, giving us a powerful window into our design's behavior. We expand the test bench hierarchy to access all our signals. Let's pick up the clock signal first, followed by the reset signal to track initialization, and we append the count bus to visualize our counter output. A quick zoom to fit brings the entire waveform into view. Here we can clearly see the counter incrementing sequentially with every clock edge, exactly as designed. Let's zoom in for a closer inspection of the timing. At this level of detail, we can precisely verify each transition and confirm the counter is behaving correctly, cycle by cycle. With our simulation verified, we can close GTK Wave and move on to synthesis. The waveform analysis in GTK Wave is now complete. Let's move on to running Yosys to synthesize the Verilog design. For the final step, we kick off synthesis by running Igny run Yosys with our custom TCL command script. And just like that, Yosys executes the full flow, mapping our design to the NAND gate cell library and generating the synthesized Verilog output. That wraps up running the Yosys synthesis process. Now let's review the output files and properly exit the tool. And just like that, our synthesized output, synth example, appears right in the Explorer. Let's open it up to review the gate-level Verilog netlist Igny has generated for us. We head back to the terminal to wrap up our session. A simple Igny exit command is all it takes to cleanly close the workspace. And we're done. A complete Verilog simulation and synthesis workflow, all powered by Igny. With the synthesis output reviewed and the tools closed out, the full flow is complete. You now have a working path from Verilog source to simulation and synthesis using open EDA tools. Good luck with your next design.